Hello all, my name is Janelle Sam and I am a sophomore in the Department of Biology at SUNY Old Westbury.
Hi, everyone. My name is Alisha Ulloa, and I am a freshman in the Department of Psychology at SUNY Old Westbury. Today, we will be presenting an assessment of taurine as a neurotropic in aged male rats in the attention set shift test. In the field of aging, many pharmaceutical companies are looking for drugs that can maintain people's cognition as we get older. Another term we use for cognition is frontal executive function. This refers to flexibility, working memory, the ability to adapt to situations, attention, and goal-directed behavior. These functions are known to decline or get worse as we naturally age. This is a major problem because by the year 2050, we are expecting to have a large number of aging populations growing. We will have higher rates of elderly people with dementia and Alzheimer's disease that will need help and supports that are very expensive. Taurine is a GABA A receptor agonist and it increases inhibition in the brain. It is important to note in the aging brain, the main inhibitory neurotransmitter, which is GABA, and when it is reduced, it is responsible for poor decision making due to impulsivity. Therefore, we hypothesize taurine will be an effective treatment for cognitive functions in aging. This is the first study that has actually used a frontal executive functioning test in an aged rodent model to evaluate whether taurine can serve as a neurotropic. A neurotropic is a cognitive enhancing drug. Although we are using a rodent model to explore what may be happening in humans, there have been good reports that show data from frontal executive functions in rodents have similar brain regions that share the same systems as in humans. To test our hypothesis, we will be using the Neurothin-Brown attention set shift test. Here in the middle, we see the translational and comparative cross-species neuroanatomy of frontal executive functions. On the left, we have the human brain. We have Brodmann area 32, which is responsible for rational thought processes, social and or contextual judgment. We also have Brodmann area 25 that is responsible for memory formation, self-esteem, and emotional balance. Area 32 is directly linked to the prelimbic system, and area 25 is directly linked to the infralimbic system in the rat's brain.
With the methods, the subjects that we used were male long Evans hooded rats that were aged to about 1 year of age, which is similar to about 60 years of age in human years, and were given tap water with or without taurine for 1 month prior to being tested. For the food restriction protocol, it was placed 2 weeks prior to the ASST testing, and the rats were individually housed and given 4 food pellets per day to maintain 80% body weight. The food restriction was placed to ensure stable motivation before testing. Habituation, day 1, the rats were able to habituate to the testing environment for 60 minutes, given a 60-minute break, and rehabituated again for an additional 60 minutes. For dig bowl training day 1, the rats remained in their individual home cages and an acrylic bowl containing dustings of crushed Fruit Loops was placed in their home cage. Training began when half a Fruit Loop was placed in the middle of the bowl and slightly covered with shredded paper. Once they were able to retrieve the Fruit Loop 6 consecutive trials in a row, we then added additional paper to be able to develop an adequate digging behavior. As you can see in the figure down below, this is how much additional paper we would add in each of the trials to develop this digging behavior. In simple discrimination, day 2, rats explored both bowls with Fruit Loops covered in shredded paper to ensure reliable digging for 4 consecutive trials. Afterwards, rats are presented with their first simple discrimination task for training, also known as medium discrimination, short for MD. For this training phase, there is a bowl with shredded paper and another bowl with styrofoam and the Fruit Loop inside. Now the rat will have to make that cognitive decision to realize that rather than the Fruit Loop being in the shredded paper, it is now in the styrofoam. For odor discrimination, also known as OD, we keep the mediums the same with the styrofoam, but now we place 2 odors of cumin and paprika, and the rat will now have to be able to realize or use that cognitive recognition to realize that the Fruit Loop will be in the paprika odor. For testing phase day 1, with simple discrimination, also known as ASST, we changed the mediums to sand and we changed the odors to Texas cedarwood and white thyme. Now the rat will have to realize that the Fruit Loop is in the Texas cedarwood odor. For the complex discrimination, also known as CD, we changed the mediums to gravel and white beads, and the rat will still have to follow the Texas cedarwood odor to be able to obtain the Fruit Loop. For complex discrimination reversal, also known as CD reversal, now the odor will be switched to white thyme, and the rat will have to make that cognitive switch to realize that the Fruit Loop is in the white thyme odor. For complex discrimination reversal, for testing phase day 2, this is just a test that they still have the recognition to be able to realize that the Fruit Loop is in the white thyme. For intradimensional shift, also known as ID, we change the mediums and the odors, and now the rat will have to follow the odor of nutmeg. For intradimensional shift reversal, though, they now have to follow the odor of rosemary, and they have to use their cognitive functions to be able to realize that the Fruit Loop is in the rosemary. For testing phase day 3, we still are testing their cognitive functions and seeing if they can use their recognition to be able to realize that it is still in the rosemary to fruit loop. For extra dimensional shift, also known as ED, rather than following the odor now, they have to follow the median. So for the first one, they follow the dirt, and for extra dimensional shift reversal, they will follow the mulch. For the results, we realized that taurine treatment reduces decision-making latency and trials to criterion behaviors to levels of a control young rat during MD and OD training in the ASST. The x-axis is showing the ASST training, and the y, the latency in the trials to criterion. In Figure A, you see the blue represents the control young, the black the control old, and the gray the control old plus taurine. As you can see in Figure A, you see the control old had a higher latency time or had a higher reaction time. In Figure B, you see the same thing, but you also see the control old had higher trials of error, or they took more trials to be able to obtain the fruit loop. For the control young and control old plus taurine, you're able to see they have comparable results, showing the reversal of the deficits in the frontal executive function. In the data, it is also showing the mean and standard error of the mean for each bar graph from a one-way ANOVA. Take into account that 66.67% of control old rats failed the training phase, and the remaining 33.33% could not complete the SD to continue the ASST. Our second part of the results are showing that taurine reversed deficits in the frontal executive function due to aging and made older rats perform the ASST equivalent to younger rats. As I said before previously, the control old were unable to make it through the training, and they were also unable to make it through the SD, which is one of the first stages of the ASST. So we were unable to get data on how they would actually do through the ASST stages. But as you can see, the control young and control old plus taurine had similar latencies and similar trials to criterion, showing the reverse in the deficits in the frontal executive functions due to aging. In the data is also showing the mean and standard error of the mean for each bar graph in a one-way ANOVA.
Summary and conclusions. This present study is the first to report using a clear aging model in rats that taurine treatment given in the later years of life can prevent the naturally occurring age-dependent declines in frontal executive functions. For example, attention, cognitive flexibility, adaptive responding, working memory, goal-directed behaviors, and their associated motor planning using the ASST. These neuroprotective effects in recovering the ASST frontal executive dysfunctions in older rats supports the claim that taurine may also serve as a neurotropic compound as an explanation for its neuroprotective properties. The improvements in frontal executive functions observed in older rats treated with taurine reversed their frontal executive profile to that of a younger rat. For example, a comparison of having the working memory of a 6-month younger rat. All the taurine rats completed the ASST, unlike their age-matched counterparts. Moreover, taurine treatment also sped up the cognitive information processing speed in the older rats' decision-making profiles observed in their latencies. These findings provide new insights into how taurine might serve to increase better rates of GABAergic inhibition in age rats. It is well established that taurine increases GABA A receptor inhibition, and this inhibition is critical for normal cognitive processes. Aging is associated with reduced GABAergic tone in the brain, and perhaps taurine is reestablishing more GABAergic tone in older rats. This would explain why and how the older rats have frontal executive profiles that resemble younger rats. Study limitations and future directions. The present study only evaluated male-age rats, and these findings may not be observed to occur in the same way in female-age rats. More work is needed in order to establish the aging and sex-based differences in frontal executive function and the role taurine might play in females as a neurotropic. This current study suggests, at least for males, that taurine may serve as a viable neurotropic for increasing more efficient and accurate frontal executive functions in age rats. Whether this finding is generalizable from rats to humans seems promising, but requires more testing and supporting translational evidence. Nevertheless, this is the first study that offers an approach to use taurine specifically as a neurotropic to improve frontal executive functions through the ASST in normal rats that only experience the natural effects of aging. There are many reports of taurine showing neuroprotective effects in neurological, psychiatric, and other developmental disorder/disability models, but less is known about its neuroprotective role in the aging brain. More work in this area may complement and or supplement what has already been reported to update the field on the prospects of taurine psychopharmacotherapy and its potential therapeutic value in humans. Here are our references.
We would like to thank our mentors, Dr. Nurit and Amanike, and the SUNY Westbury CSTEP/LSAP department for their support and ongoing efforts in providing opportunities for underrepresented minority and financially disadvantaged students within the STEM fields. This work could not have been completed without your support. We would also like to thank the SUNY Westbury FDG awarded to Dr. Nurit and the SUNY Westbury CSTEP stipends awarded to myself, Alisha, and Michelle Vasquez. Thank you for your time, and if you have any questions, please feel free to ask them now.